Hello students, welcome to the class. Today we will see the next part of the classification of elements and periodicity in properties, in which we will cover section 3.3 and 3.4. Disclaimer: the images and text and other materials used in our presentations are for educational purposes only. We respect the intellectual property rights of the original creators and owners. If you are the owner and have any concerns or issues, please contact us at sathee@itk.ac.in and we shall remove the content immediately. Please note that parts of the content may have been generated using generative AI, which is experimental. Our today's objective would be to understand the periodic law and look at the nomenclature of the elements whose atomic number is greater than 100. So the NCERT sections 3.3 is of modern periodic law and the present form of periodic table, and the nomenclature of elements with atomic number greater than 100. First of all, we will try to understand that what is the cause of periodicity. In yesterday's class, we discussed that atomic weight was not good for classifying the elements. Okay. So what was concluded in that class? That we should move on to some other thing which is able to put a good classification of elements. So it was seen that if you keep your elements in increasing order of atomic number rather than the atomic weight, then there was a pattern that was seen, which was repetition of the properties of the element after regular interval, and second thing, similar outer electronic configuration. Two things, right? So Mendeleev took the properties as the best thing to classify it, but in that process you have to look at each and every property, and that is very difficult. He took the second thing, which was atomic weight, and he obstructed that same point. So to keep a more simpler version of that, we took the atomic number, and the result of it were great. First of all, the properties of the elements are repeated, means the classification was in accordance with their properties without any change in the order of the atomic number. Second thing, similar electronic configuration we are seen for the outermost shell if they are placed in the same group. Now, these two observations cleared it that the cause of periodicity is there in the atomic number and is due to the repetition of similar electronic configuration. So most of the reactions or most of the properties that you see around are dependent upon the electronic configuration, because they share the electron, they make it a covalent bond, they make it ionic bond. So all of this are dependent upon the electronic configuration, and especially the outer one. So we can say that the cause of periodicity is what? Is your similar outer electronic configuration. We can look at the examples also. So here is an example for you. We are taking the sodium and potassium. If you look at their outer electronic configuration, so they both have one electron in their outermost shell. As a result of this, they are showing same chemical properties. One reaction is shown here to resemble that. You can see that your sodium reacts with water vigorously to form a sodium hydroxide, which is NaOH. Now the potassium, which has the same number of electron in the outermost shell, it also reacts vigorously with water to form the potassium hydroxides. Now what we can say, that due to this similar outer electronic configuration, which is one electron, they both are forming corresponding hydroxides on reaction with water. Now, keeping this discussion in mind, we can now formulate our modern periodic law. So this thing was done by Henry Moseley in 1913, and he used the X-ray spectra. So we have seen what is emission spectra, what is absorption spectra. So he used the emission X-ray spectra. Why I am telling it X-ray spectra? Because he used the X-rays for it. You know that your absorption or emission spectra are done with the help of electromagnetic radiation. In this case, Henry Moseley took the X-ray part of the electromagnetic radiation out of the whole spectrum, and he plotted a graph between the emitted X-rays frequency. So he took the root of that frequency and plotted it against the atomic number and got this graph. You can see that as the atomic number is increasing, your emitted light has a greater frequency. So your frequency, or you can say the root under frequency, is increasing with the increasing atomic number. So this plot clearly shows it. With the help of this observation, he said that atomic number is the most fundamental property of any element. So he didn't focus on your atomic weight, he focused on the atomic number. He plotted a graph between the root of the frequency emitted in the X-ray spectra and the atomic number, and got a linear line. Therefore, he said that okay, atomic number is the most fundamental one. With the help of this, he predicted the modern periodic law as the physical and chemical properties of the elements are periodic function of their atomic number. So this is the accepted form of the modern periodic law, which is in accordance with every property. So why did he took the square root of the frequency? That's a way to define the equation. So there is an equation basically which goes like this, that root under nu is equals to a z minus b. Okay, this is the main equation, a square z minus b. So if you just multiply a with z and a with b, you will get a final equation, y is equals to mx plus c. Okay, and that is the reason you are able to see a negative intercept. You must have seen right now that the graph was rising from the downside, so it has a negative intercept. Yeah, and due to that equation, so I will not go back into the part of the derivation of that equation. So in accordance with that equation, he took the graph between the root nu and the atomic number. Now, on the basis of this, he formulated the long form of the periodic table. So we will look at its structure. First of all, there are two things in the long form of the periodic table. The first one is periods, which is the horizontal row, and the vertical column, which is the group. So here is a pictorial representation of that. So you can see the down arrows, the marked one, which are indicating that your groups are what? They are vertical columns, starting from the top moving to the bottom. Similarly, if you took the periods, so they are starting from the left and moving to the right. So that is shown by the horizontal arrows. So remember this point, this is very important. I will use this terminology of groups and periods term by term. So you must remember that groups start from top and moves to bottom, and periods start from the left and move to the right. Okay. Now we will try to go more deeper into this groups and periods one by one. So what is the significance of this group? Is that we keep those elements in the same group which have a similar outer electronic configuration. And we name those groups as 1 to 18. Now there was a previous notation for it which includes 1A, 2A, 3A, 4A, 5A, moving on to 7A, then starting from 8. So this was removed, okay? And now we simply count the groups as 1 to 18. Now why I am saying that the elements which have the same outer electronic configuration will be placed in the same group? We can understand that with the help of this example. So 3 elements are there, right? 3 elements are there. So one is lithium, second is potassium, and the third is second is sodium, and the third is potassium. So they have 3, 11, and 19 as the atomic number, whereas the electronic configuration is 2, 1, 2, 8, 1, 2, 8, 8, 1, and their outer electronic configuration is 2s1, 3s1, and 4s1. Okay. Now they are placed in the same group. What is the reason behind it? Because they have the same outer electronic configuration. You can see it very clearly. They all have S1, S1, and S1 in their outermost shell. So this clearly indicates that your lithium, sodium, and potassium falls in the same group. So remember this point. This is very important. If the outer electronic configuration is same, they will fall always in the same group. And how do we name it? We name it from 1 to 18. Now moving on to the periods. There are 18 groups and there are 7 periods in the periodic table. Now what is the significance of this period here? So when you write the electronic configuration of any element, then the highest principal quantum number present in that electronic configuration simply represents the periodic number. How? Suppose you are talking about hydrogen. Electronic configuration is 1s1. What is the highest principal quantum number possible in its configuration? It is 1. So it will belong to the period 1. As simple as that. Similarly, if I talk about the carbon, it is 1s2, 2s2, 2p2. Now again, the largest principal quantum number in its electronic configuration is 2. Therefore, it will belong to the period 2. You can talk about sodium, iron, iodine, and any other element. All of these will follow the same type of methodology to assign the period number. Now there is an important representation of the electronic configuration which is shown for the iodine. You can look at here and say that why krypton is written in the box before writing the outer shell electronic configuration. So this is symbolizing that you can write the electronic configuration of krypton first, and after that you can put the given thing which is 4d and 5s2 and 5p5 to write the whole iodine electronic configuration. So this is just a way to symbolize the electronic configuration of iodine in a shorter way. Again, its highest principal quantum number is 5, therefore it will fall in the 5th period. Sorry. Then this is the number of elements that are present in each of the period, or I would say the theoretical number, because in the 7th period there are less than 32 elements present, because some of them are not discovered, but they are although named, but it is not being fully identified. I will not go into it what are those elements, but you should remember that in the first period 2 elements are there which are hydrogen and helium. In the second period 8, third also 8, in the fourth 18, fifth 18, sixth and seventh 32 elements are there. So this is the counting. It's very easy to remember. Just remember this point: 2, 8, 8, 18, 18, 32, 32. As simple as that. Now there is a unique thing which you will see in the upcoming image, that a set of 14 elements which are said to be the 6th, which are said to be of the 6th and 7th period, they are placed in a separate panel at the bottom, and they are termed as the lanthanoids and the actinoids. Okay. So if you look at the long form of the periodic table, you can see them written at the bottom panel. So there is a bottom panel above which it is written F, inner transition element. So they are of the 6th and 7th period. So remember it, lanthanoid is of the 6th period and actinoids is of the 7th period. Now if you look at the 6th period, there is a simple counting given 1, 2, 3, 4, 5, 6. On the 6th period you have the cesium, which is CS, barium, Ba, lanthanium, La, which has an atomic number of 57. After 57, 72 is written. Now the missing atomic numbers are present at the bottom panel in the first row. Cerium, which is starting from the 58 atomic number and ending up to the 71, which is luteum. Similarly, if you look to the 7th period, just count from the top 1, 2, 3, 4, 5, 6, 7. There is francesium, then radium, then actinium. Then after 89, again some atomic number are missing. So there is a gap of 14. So those 14 are again placed in the second row of the bottom panel, which is starting from thorium, having an atomic number of 90 and ending at 103, which is lawrencium, which has a symbol of Lr. So remember this part always, that 14 elements are placed at the bottom. And now you can also look at the periodic table and say that what is the group number and the period number. So group number is written at on the top side 1, 2, 3 and ending up to 18. So go from left to right, you can see at the top, and the previous notation is also mentioned there, which is now not used at all. Okay, so 1, 2A, 1A, 2A, 3A, 4A. If you want, you can learn it, because sometimes questions are asked based on this previous notation in your periodical exams in the school. So I would suggest you to remember these notations also, including the latest one, which is a simple one. You don't need to remember it also, but the previous one is somewhat changed. Starts from 1A, ends on 7A. Then there is a 8 group which includes 8, 9, 10, and then is 1B, 2B and so on, move on to 0. Okay. Now here is a very easy question for you. What is the period number of carbon in the periodic table? 4 options are given here, 1, 2, 3, 4. So you have some time to solve this question. Your time starts now. It's very simple. Just look at the periodic number. Yes, the correct answer will be 2. How we have solved it? I said you that you should look for the highest principal quantum number. Now, this is an easy example to do, but when you will meet with a element that has a very high atomic number, there it is very difficult to decide that in which group or which period it is falling. But if you are able to write its electronic configuration, then you can simply look at its highest principal quantum number and identify that it belongs to which period. Now questions are asked from here in the PYQs question. So if you write the electronic configuration of carbon, you can clearly see that the highest principal quantum number is 2. Therefore, the carbon will lie in the period number 2. Then the next question, which of the following pairs of elements have similar outer electronic configurations and therefore belong to the same group in the periodic table? Options are A, oxygen and sulfur, B, nitrogen and carbon, C, boron and fluorine, D, neon and sodium. Again, you have to look for the similar outer electronic configuration. For that, you have to look for the same group. So, you have some time to solve this question. Just write the electronic configuration of each of this and look that which of the following pair have same outer electronic configuration. So the correct answer will be option number A, oxygen and sulfur. How do we identify it? Just write the electronic configuration. For oxygen it is 1s2, 2s2, 2p4, and for sulfur also it is 1s2, 2s2, 2p6, 3s2, 3p4. Now both have a same outer electronic configuration, which is s2 and p4. Therefore they will fall in the same group, and if I talk specifically, then it will fall in the 16th group of the periodic table. Then moving on to the next section of NCERT, which includes the IUPAC nomenclature. So at the time of discovery of elements, it was seen that first of all your elements were given a name according to the discoverer, and IUPAC was approving that thing. But an element which has an atomic number of 104, it was claimed both by the Americans and the Soviets. Now Americans named it Rutherfordium and Soviets named it a different name. So to avoid this kind of debate situation, IUPAC said that okay, before assigning an official name to any element, we will assign a temporary name. Now how do we assign it? So it is based upon the numerical roots. We will look on it now. So if you are doing so, you have to follow notations for the IUPAC nomenclature of the elements, and its roots are given in the following way. If the number is 0, write nil. If it is 1, write un, and also remember its abbreviation. So this is the most important point. Remember its abbreviation. Similarly for 3 it is tri and the abbreviation is T, and so on. So you can look at it. There are 10 names of it, and their related abbreviations are given on the at most right table, at most right column. So if you have to name a compound, just simply put them in order of the digits. Suppose it is starting from a number 1 and it is ending at a number 4, and there is 0 in middle. So simply take their roots given here and put them in that order, and at last put IUM at the end, and you will get your IUPAC name. Now again, this is applied only to the elements with atomic number greater than 100, and it is according to the nomenclature. Here are some examples which is shown here in the table number 3.5. So if you are writing it for the element whose atomic number is 101, so for 1 you will write UN, for 0 you will write NIL, for 1 again you will write UN, and at last you will put IUM. Now the important part is there, which is the symbol. For 1 it is UN and the symbol is U, for nil the symbol is N, and for again un the symbol is U. Therefore its periodic, I would say, the element symbol will be UNU. Now there are several atomic numbers are given, which are given, and accordingly their symbols and nomenclature is also given. Apart from this, the IUPAC official name is also given. So these elements have their IUPAC official name, but although it has the one, you can use the IUPAC nomenclature. So the first one is Mendelevium, Nobelium, Lawrencium, Rutherfordium, Dubinium, Seaborgium, Borium, Hasmium and Mithrium. So these are the remaining elements which ends up at 118. So Darmstadtium and then Rontagium and so on. So you must know how to write the IUPAC nomenclature, and it's very easy, I guess. Here is a question for you related to that part. You have to write the IUPAC name and symbol for the element with atomic number 120. Your time to solve this question starts now. Okay, time is up. So what will be the name and symbol? The name would be unbinyllium and the symbol would be UBN. So it's very easy to solve. Just write the roots accordingly for 120 and you will get your symbol and name both. So this was all for the theory part. Now we will do the DPPs related to it. So just wait for a while. I will come back with the DPPs.